Professor Fink earned his PhD from the University of California, Berkeley, where he worked under the guidance of Bernstrom, Fels, and Frederick Harvey. Following his doctoral studies, he held a postdoctoral position at North Carolina State University before joining Team Mary at London, where he currently serves as a professor of pure mathematics. His research has been supported by EPSRC, and he has contributed to the academic community through his roles on the editorial boards of the Bulletin and Journal of LMS, as well as Theoretical Computer Science A. Notably, he co-chaired the program committee for the Power Series and Algebra Combinatorial.
It is shared from that year.
Why did you take you this?
It might be from that year.
Okay. Well, please join me in welcoming Professor Fink.
My thanks to June for that wonderful display of web searching. I forgot to
That's
ChatGPT. Oh, ChatGPT. Oh, very good. It worked. The web search for the lawyer. Okay. Yes.
The free version of ChatGPT.
Free version. All right, so welcome everyone. The exciting thing I've done recently is this paper with Andy Berget, where we prove David Speyer's tropical F-vector conjecture. But Andy Berget was here in the fall and gave a few talks on this stuff. So I talked to Andy and asked, well, what should I talk about? And he said, I never talked about section 6. Why don't you talk about that? Section 6 being like the gruesome combinatorial heart of the whole thing. So at least
not talk about.
that's what you talk about. Okay, so I'm the patsy here, but at least I had the clever notion to ask for 2 hours. Okay, so hour number 1 today will be perhaps the more familiar hour to those of you who've seen either Andy talks on this or me talk on this in other venues, but I want to get to the introducing the diagonal truncation, the main matroid, and then in the second hour, I want to do this business, like some fan displacement rule intersection graph goodness. Okay, so let's start by, as both titles tell you, this is a talk about, David Speyer's g-invariant. So let's start by introducing that. So I want to give, let's set some conventions first. So this is one of the Speyer's g-invariant. This is a matroid invariant, and my matroids are going to be of rank R on n elements. So it's because some people prefer the projective indexing where there's n-1. Rank R or letters like R on the set 1 through n are the kinds of matroids I'm looking at. And my main example, of course, will be representable ones, which I like to think of through linear subspaces. So this is also potentially a convention. One could associate the dual of the thing I want to associate. So given a linear subspace, and I may as well work over C because our proof techniques are genuinely characteristic 0. So let's just work over C. Then I want to associate a matroid to it. And the way I want to do this is that the bases are given by it's the hyperplane arrangement point of view. The bases are given by the restriction of the linear functions to L. So, so B a subset of N, where if I look at the saved coordinates on here are called X, I look at Xi restricted to L, and this should be a basis of all the linear functions. So this is the same perspective as you get if I look at the hyperplane arrangement that I get by intersecting L with the coordinate hyperplanes in here, right? So inside L, L sits in C to the n somehow, And then you have a collection of coordinate hyperplanes, you know, x1 equals 0, x2 equals 0, etc. You know, some can be coincident. Maybe some could not be hyperplanes indeed, and you can see which ones are bases from the hyperplane arrangement, the matroid of the hyperplane arrangement in the usual, more common convention. Okay, so I want to define Speyer's g-invariant for such a thing. Not the way Speyer first did it or the way I did it in my first paper with him, but using the Berget Eur Spink Tseng apparatus of these tautological bundles. So I'll start with the geometry for the realizable case of that. So let's take the complex n torus, which I want to act on c to the n. For what's essentially sign convention reasons, we're going to use the inverse scaling action. But for most of what I'm going to do now, I'm just taking orbits and so on. So it doesn't particularly matter if I use the expected scaling action. The inverse scaling action, if you want to track the signs, I'm using the inverse scaling action. Okay, so now given this, if I've got my linear space L, I can make a pair of vector bundles, torus equivariant vector bundles, where L is going to sit as one of the fibers. Okay, so what should this look like? Well, over the identity, I want to do, I have this sequence, I can put L and C to the n, and like this, I have this exact sequence of vector spaces, and by putting this over the identity in the torus and just taking torus orbits everywhere in here, I get a sequence of vector bundles where now I'll have the trivial C to the n bundle in the middle with trivial torus action. Let's put it for this T. This I'll call the sub bundle for L. And this I will call the quotient bundle for L, tautological sub bundle, the tautological quotient bundle. And right, I take this and just act by T inside here, and I get, you know, this subspace moves and the corresponding quotient moves. And okay, well, because I have the diagonal scalars in here, those fix linear spaces, so I can mod out by the diagonal spaces on the bottom, so the diagonal torus on the bottom, and -1 torus down here. And then I can look for a compactification on which this will extend to a well-defined exact sequence of bundles, and these things will extend to bundles, and the permutahedral toric variety, which we've probably run into here, gives us such a compactification. So in fact, I can, forgive me erasing, but really I kind of, okay, if I want to think of this as being the big torus inside Xn, which will be a notation for the permutahedral toric variety. The permutahedral, that's the convex hull of an Sn orbit, normal to, okay, so like, well, permutahedron or, you know, S and whatever you call this, the nth permutahedron, the n-1 dimension permutahedron. So some nice proper smooth toric variety down here. We're going to get, you know, move away from this fairly quickly in the proceedings, so I won't spend a whole lot of time on the geometry of this, but probably it's shown up in seminars here before. Okay. So it is, I guess, in this formulation, due to Berget, well, Berget Eur Spink Tseng. I think it's last year that appeared. Well, that you can make a sequence of vector bundles like this. Oh, I didn't write. Equivariant vector bundles. You can make a sequence like this of vector bundles, and then if I want to look at a non-representable matroid, a matroid which doesn't correspond to any such L, then I can make some kind of surrogate for this sequence and do some of the kinds of computations that I'd like to do if I had this sequence. The surrogate I'm going to have is a class in torus equivariant K-theory. I know there's some people here who have been asking everyone, what's the deal with K-theory? So, okay, for these purposes, maybe, well, I'll write down a statement and I'll say a little bit about the deal with K-theory. For any matroid M, that are supposed to emulate the things in this sequence when I don't necessarily have a linear space. They are going to live equivariant algebraic K-theory of the base, which I've taken it from the property, and they should match. So that if I have the matroid of a linear space, it should match with the actual bundle associated with that linear space. And if I have, all right. So if you're the kind of person comfortable with some cohomology theories like the Chow ring or I don't know, Dirac cohomology or something, but not with K-theory, I guess for these purposes, it's enough to say that K-theory is some kind of cohomology theory, which is nice in that vector bundles have classes directly in it rather than having to work through characteristic classes of some sort. So it's natural to, take a vector bundle and associate a class to it, like these. Torus equivariant just means, we're modeling things that are torus equivariant, tracking some data about the torus action. This is, again, since I'm heading for the combinatorics, I won't say too much about setting up the algebraic geometry, but this is a completely combinatorial ring. And so it's worth saying that by equivariant localization, kind of things I think Bill may have talked about last week. Yes. Yes. Okay. You can have an equivariant localization presentation of this ring. So this is a ring that sits inside. Okay. Well, what is it? Like fixed points. There's n factorial fixed points here. So it's like it sits explicitly inside just the direct sum over permutations in Sn of a copy of this ring for a point, which is a Laurent polynomial. So this data is really a fairly explicit, tuple of Laurent polynomials with some compatibility conditions that define the image of this embedding. And so this is some combinatorial data that you can associate to any matrix. It comes from lexicographically first bases. If you have a permutation, you pick the lexicographically first basis, take the sum of the t's or do some game like that, and that's how we get these classes.
They satisfy what you would expect from the exact sequence relation.
They satisfy what you expect from the exact sequence
Some of
relation.
them is
So yeah, the sum of them, right? So okay, I guess the sum of these two is going to be the class of that. If you have expectations of what should happen here, it all works out here. So for example, the class of S of M plus the class of Q of M is just going to be the class of this guy. Sorry, with not the trivial action. I think I said trivial action, but I mean this inverse scaling action. Okay, and the class of this guy with the inverse scaling action is just the sum of the inverse characters. So at each fixed point, you see the characters in your Lex first basis in this one, and the characters in your other basis in this one. And you sum up to all the characters. This class. Okay. So we have these objects. And so if I do a kind of algebrogeometric computation with the S and the Q that happens to descend to K-theory that can be reproduced in the setting of K-theory, then I can try to interpret it for an arbitrary matroid. And Speyer's g-invariant is a computation of this form. So here's how that looks. I will motivate this after I define it. So just to get the, so this is not the original definition, but it's kind of reinterpreted in terms of these objects. I like that paper. So Speyer's g-invariant is this thing. Okay, it's going to be a polynomial univariate in a variable that I'll call t. Different to these t's, apologies. And all right, there's some fiddling with signs. So -1 to the number of components, connected components of M. And then it's just going to be a generating function up to some signs for holomorphic Euler characteristics of exterior powers. I should put this whole thing in a class because it's going to be one of these matroid K-theory classes. Exterior powers of the S bundle, tensor exterior powers of the dual of the Q. Okay, so if I hadn't put a class there, right, this would be, these exterior powers would be bundles. You'd tensor them together, get a bundle. You'd take its Euler characteristic, that would give you some number. But this is one of these computations that you can do in the K-theory ring. There is a Adams operator that will turn the class of a bundle into the class of its exterior powers. That is just an elementary symmetric polynomial. If you do it in the localization setting, then you multiply them together, and then you push forward to a point that implements this Euler characteristic, and that gives you some number which you can do completely combinatorially with these tuples of polynomials in rings. So this is a description for some explicit process you can do in the K-ring. You get integers, a polynomial with integer coefficients for every matroid. So with a geometric meaning if L is representable, but definable in any case.
That has a bit of asymmetry, right? Because like S, let's say that rank of S is K and then rank N minus K, so some.
Right, so eventually these, well, okay, so when, for instance, okay, I used R for the letter for the rank, so S has rank R, so this will vanish once K gets greater than R. This will vanish once K gets greater than N minus R. So, there is a symmetry here. There's sort of dual symmetry, right? So has the degree of this thing is bounded by, well, both of R and N minus R. Once either of those vanish, then these coefficients here will be 0. So, in fact, it turns out, because duality more or less exchanges these things up to the Cremona map, you also can say that G of M is equal to G of M dual. So, this is some kind of, the thing you were calling an asymmetry, I would call it a symmetry. It's saying this thing is insensitive to whether I dualize the matroid or not. In either case, it's the lesser of the rank and the co-rank that I'd expect to see as the degree here.
Can you motivate this definition? Like what?
Yes, that's the very next thing I want to do. Why? What did I do all this for? Okay, this came from David Speyer's desire to find extremal combinatorics of matroid subdivisions that he got into through tropical geometry. So it's supposed to give bounds on enumeration of cells, face numbers, you can use that word, face numbers, in matroid subdivisions. So I guess there are two facts of this that make it useful for this. It's supposed to be measure-like. It's a valuation. Some people will know the word valuation. It's supposed to add up in matroid subdivisions. And so if you can say that each summand is at most, at least so large, and they sum to a given thing, there are, at most that many summands. Let me write that down properly. So the one thing I want to say is, two facts. If you've seen valuations, I'm just going to twist the sign here, right? So this is, all right, what does this mean? Given any matroid polytope subdivision, there's an additive relation for the values of G, and what this means is that if you're expecting to do inclusion, exclusion on the polytopes, you don't do that, you keep all the signs plus. It's like you're considering the open polytopes. So I think, the matroid polytope I can draw, it's the octahedron, U24. I can split that into two matroid polytopes by taking the top square pyramid and the bottom square pyramid. These are both matroid-based polytopes. And I'm thinking these as open things. Well, I haven't covered the interior of the octahedron with this and this because I'm missing the interior of the square. So I should also add in the interior of the square. And so for any cell complex where the total space and the cells are all matroids, I want to have an additive relation like this. Well, I do, in fact. Okay, that's a property this thing has. And the second fact we like is that, so if M has K connected components, then G of M is some positive number times T to the K plus higher terms. And sometimes G of M is just T to the K. Well, maybe okay. G of M equals T to the K is attained. But the thing is, the kth coefficient of this is supposed to be counting the contribution from matroids with K connected components, and these are ones whose polytope is of codimension K. So if you have a subdivision, the maximal things, I'm calling that codimension 1 because it's n-1 dimensional in R. But the maximal things correspond to the coefficient of T to the 1, and every one of them makes a positive contribution. So the T squared term, every, codimension 2 thing makes a positive contribution, and so on. And so if we could say that these higher terms are also non-negative, then we would say, well, the sum of all of these contributions gives you then, the sum of these contributions is known. I evaluate G at the big thing. That's the sum of all the contributions from the pieces. Each piece contributes at least T to the K. So the coefficient of T to the K is a bound on how many pieces there are. That was what this was for, right? So, and so kind of the big conjecture that would complete this argumentation, which is the thing that we proved, is that in fact, all the coefficients are non-negative. And once you have that, right, you know that every piece makes a contribution to the T to the K, and so you can bound the number of pieces. All these things together will imply that the number of dimension K faces in a subdivision of M is bounded above by the T to the K coefficient in the valuation of the big M. So it's some kind of measure which can make this bound argument. That's the reason why it was introduced. And indeed, for example, G of this thing, this octahedron actually is 2t plus t squared. This actually is a finest subdivision. You can get two top dimensional pieces and one wall, which is this coefficient 2 and this coefficient 1. So this is actually the finest way you can chop this thing up. A finest way you can chop this thing up into matroid polytopes. And that's what this is supposed to be expressing. A finest way you could chop this up might get as many as two top dimensional pieces and one piece of the next dimension down. Cool. All right.
So sometimes there will be no subdivision.
Sometimes there will be no subdivision, right? Sometimes the bounds are just like all you can not subdivide, but still this G is going to have large numbers in it. So it's the bound is not always tight. It's tight for the uniform matroid, for instance. It's tight for the hypersymbolic. It's tight for Richardson matroids. It's tight for various classes of matroids, but not always. It's hard to tell.
Can you remind the definition of matroid polytope subdivision?
Oh, okay. Geez, yes, I will certainly do that. Yes. Definition, okay. This is the first part of the talk. Okay. The base polytope of a matroid M is the convex hull of the indicator vectors of its bases. So this is meant to be the basis set system, and this is the 0, 1 indicator vector. And so, okay, this thing I was drawing here. Okay, so this is supposed to correspond to U24. This is supposed to be P of U24. Every size 2 subset of 4 is going to be a basis of this. So I take, 0, 1, 1, 0, 0 is the indicator vector of 1, 2, 1, 0, 1, 0, and so forth. This gives me a collection of vectors. Oops, I missed 2, 3. This gives me a collection of 6 vectors in R4, which all have coordinate sum 2. So I'm drawing in the 3 space, where the sum of the coordinates is 2 in R4. These 6 things form an octahedron. You can tell when something is a matroid polytope by looking if all the edges correspond to single exchanges. So I shouldn't have an edge that goes like that, because 1, 2 to 3, 4 is not a single exchange. Okay. So yes, that's what a matroid polytope is. A matroid polytope subdivision is a cell complex where the cells are these guys and the total space is one of these guys. And then this thing was introduced by Speyer, trying to make this extremal argument. What's needed to make it is this property that the coefficients are non-negative. All right. So that is.
There's some reason that this particular, could there be other expressions which are also co-valuations, or is there some co-valuation one could come up with?
Yes. Okay. So being co-valuative means something like being linear on the matroid Chow ring or something like this, or being valuative means something like this. It's a linearity property, and okay, this is maybe this doesn't look linear in M, but this turns out to be linear in M in the requisite way. This looks quadratic. Okay, so that's not very enlightening to say, but if you like this matroid Chow ring apparatus, it's relatively easy to produce valuations or co-valuations, and that's just a choice of sign. You just do linear operations in intersection theory, multiply your class by a fixed class, that kind of thing. You'll always get a valuation. So you should think of this as a linearity property. And sort of what makes this the good choice is that like you get just a single coefficient 1 a lot of the time. Like for the pieces that should be the smallest pieces, you want to get just t to the k, not something bigger. And this is the choice that will give you t to the k for direct sum of k series parallel matroids, which is what should be the smallest pieces, kind of, if only experimentally. So that's the key one, kind of.
Does the pyramid have a bottom? Like when you subdivide?
Does
Is it
this-
closed?
this is-
Object?
I mean, yeah, this is my drawing of a square pyramid.
It has a bottom.
It has a bottom. This covaluation property, I want, I'm thinking of all of these things as open. If this is the interior of this is the disjoint union of the interiors of these three things.
Oh,
So you're always thinking of the interiors when you draw these pictures.
Yeah. If I say co, I'm thinking of the interiors. If I don't say co, which I might do out of habit, then I'm thinking about the closed things. But this is a sign convention.
so what's rigorous definition of subdivision?
Cell complex? I just mean a cell complex where all of the cells are of this form.
So the value at 1 of this, of the triple,
Again,
the value at 1 is.
the value at 1 is the total number of interior cells, or the bound on the total number of interior cells, which may or may not be tight in a given case. That's right.
The defect, when it doesn't achieve the maximum, is that?
Yes, there are defects. I mean, there are matroids which you would like to be able to subdivide and you can't. So if you do the Fano matroid, I think, or even matroid K4. So again,
One of these pieces.
one of these pieces, you cannot subdivide this any further, but here, this is t, this is t, this is t squared. That's the value I want to assign to like primitive, not further subdivisible pieces. But if I take something like the matroid of K4, this is the same, I think. It's 2t plus t squared. I think. But you cannot subdivide this one. So, right, whether a matroid has subdivisions is a subtler question than this. The bound is indeed not always tight, and there's lots of matroids out there which you'd like to think of this as cut into two more simpler pieces glued along some matroid. You can't do it.
Is there a lower bound as well?
Lower bound for a finest subdivision?
No, for the G vector condition goes this way, right?
Yeah.
Is there something coming?
I mean,
Are there lower bounds on how many subdivisions you can?
Very many matroid polytopes cannot be subdivided. in
Yeah.
that way.
Even if you expect them to be subdivided?
right. This is a measure. Think of this as volume-like or something.
I see, okay.
So, if something has, these are lattice think of it as like lattice volume of lattice polytope. If that's one, you can't subdivide it, but that's not the only criteria.
Every binary matroid has no subdivision.
Every binary matroid has no subdivisions. So, good, okay. Good, all right, yeah, I should continue taking questions until people are satisfied, because clearly I should have started with that slide, and I started with this slide instead, which was silly. Okay, any other questions? Or are we roughly on the same page now?
When you say codimension, those things look like codimension 0 to me.
Right. Okay, so yes, I am being cheeky there. Codimension K in Rn. All my pictures are of n-1 polytopes, which are just living in Rn, because all bases of a matroid have constant size, so I always have one linear condition. So kind of the whole thing I'm calling codimension 1 with respect to, this is codimension with respect to R4. So that's just me putting a fast one over on you, that codimensions are one larger than they look like they should be because of this lying in a hyperplane.
May I say just a small comment?
Please, yeah.
In case people find it useful, the linear term of G, when matrix is connected, is the beta invariant of a matroid that invented or discovered many years ago, and being of interest for other reasons. So, yeah.
Yes, even when it's not connected, in that case, both numbers are 0. Yes. So the
only subtlety is how do you define G for loops and co-loops? So that's why.
I see. Sure. Okay. Yeah. All right. So what I want to do next is say a little bit about the proof of this positivity, this non-negativity, in the representable case. Just a little bit, because what I'm trying to talk about is the gory combinatorics that underpins the non-representable case. But I want to talk about the proof of the representable case because this spits out a simplicial complex, and then we have to study that simplicial complex. So I should at least say, try to say again, you've been very good at keeping me honest, so keep it up, right? But I will try to say quickly in the next 20 or fewer minutes how the sketch of the proof of the representable. Okay. So I really have line bundles. I really have some exterior powers. Here I really have to compute an Euler characteristic. Well, the first thing you do, okay, is I generalize the problem before I start to work on it. I generalize the problem by saying, okay, here I have M and M. Let's make them different. Let's make these possibly different linear spaces. Okay, since I'm representable, I'll call them L1, L2. Well, I want to consider these things like wedge powers of, actually, I should edit myself. Okay, first step, reduce to considering the top coefficient. Second step, do that, I was going to say. Okay, first step, reduce to the top coefficient. Reduce to considering the top coefficient, which, as we just said, I'll say the rth coefficient, break the symmetry. So if n minus r is less than r, I'll just be talking about 0, but that's okay. I want to reduce to the coefficient of t to the r in g of m. This is a thing which is called omega of m in my paper with Kris and David Speyer. We do an intersection theory on Bergman-Fan kind of computation to write all the coefficients as positive combinations of these top coefficients from minors. And so that reduces the general problem to the problem for this top coefficient. So now we only have to study this thing. Okay, so this thing is, and we can reduce to m connected. Then this top thing. Okay, these signs give me a -1, and I get wedge R and a wedge R, M1 and M2. Well, it's just M so far. I haven't done it 1 and 2. And it is convenient for him doing next to say, this is a rank R vector bundle, so its rth wedge powers is a line bundle, is top dimensional. So I can dualize this using that sequence up there and write it at the n minus rth wedge power of this guy. So now I have 2 different quotient bundles. Okay. Having done that, now I want to say, let's use 2 different m's instead of just 1. This is one of these cases where generalizing the question lets us make a very useful connection which is to the Matroid Schubert variety. Vanilla Booker perspective on the Matroid Schubert variety. And we use this kind of both for inspiration of proof techniques and actually to reduce to it. Okay, so next step is take two different linear spaces, like I started to say. And look at this other characteristic for well, okay. I guess in principle, well, okay. I might want to look at any wedge powers. For now, I'll just look at any wedge powers. Okay. The reason this is important, I will say after I state what the next step is. Okay. So, due to work of Federico Ardilla, okay, that's all. You can go. See you. And Adam Booker, we can relate one of the case where one of these is aligned to the Matroid Schubert variety. How do we do that? We do a Kempf collapsing away from this bundle. So what's the idea? I guess one way to say it is these kind of wedge powers, like these wedge powers are kind of things that would arise in a Koszul complex. I could have a Koszul complex resolving my S by these wedge powers of these Q duals. And I could have take the tensor product of two such complexes and get a resolution of S tensor S by all of these tensor products of wedges of Q duals. So if I have this S, sorry, S direct sum S minus sake, if I have my S direct sum S, okay, this thing has, it's a subbundle of a 2n dimensional trivial bundle, rank 2n trivial bundle, and it has a Koszul complex resolution that includes these things. Now, this is kind of, the tool in particular we're using is called Weymann's geometric method for syzygies. But we have, there's kind of a few auxiliary results we need to show that we're in the setting we can apply this. I'm trying to get to the combinatorics, so I'm hiding what's in Weymann's geometric method for syzygies. We'll talk about it. What this says is I can take this free resolution and use it to obtain, under certain, niceness assumptions, a free resolution of what I get by projecting this into the fiber, right? Okay, so each fiber here is some linear space in here, and I'll just take the union of all the fibers within Cn plus Cn. I'll project into the fiber. Right, I want this thing to be sort of, I want to think of this as, okay, I'll write this trivial bundle as X and cross, the total space of this lives in this product, and I want to project it onto the second factor viewed as a subset of that product onto some variety in the paper. It's going to happen here. This thing is called the Kempf collapsing of the bundle. Kempf was working in representation theory where it's often used to collapse bundles like this. Okay, when you do that, you find that you get a free resolution, so the Koszul complex for this sum of the S's pushes to a free resolution of this guy involving all of these wedge products. Tensor. Okay. So in particular, the wedge product I want is like some bi-graded, in fact, it's minimal, some bi-graded Betti number, some bi-graded pore of this guy. So I have it encoded in commutative algebra somewhere. All right. It's not very combinatorial yet. I will combinatorialize it by taking an initial ideal, by doing a Grebner degeneration. Okay. Now take the initial ideal of this thing. In fact, I can use my choice of term order. Two very nice things happen. The first very nice thing is that I always get a square free monomial ideal, so I can associate a simplicial complex to it. So I'll call this ideal, call my term order W. And I'll call the ideal IW of M1 and M2. It will depend only on the matroids. And the two key facts are first, that this is a square free monomial ideal. Which means that by Stanley and Reiser, it's got the same data as a simplicial complex, right? You look at the monomials that are not in it, the square free monomials that are not in it, and that forms a simplicial complex. So I associate to this a simplicial complex. Okay, and let's label the vertices.
So Alex, if I may ask,
Yeah.
I know you said it, but this Y had L1, L2, it lives in Cn or in Cn plus?
This lives in Cn plus Cn. It lives in the second factor here. Okay, so if like, yeah, like L1 lives in X variables, L2 lives in Y variables, right? Then I have
No, I misunderstood
Yeah.
second factor because I thought you take both.
oh,
but I
sorry.
see
Second factor of this thing. Sorry, second factor of this product. This thing. Yeah, thank you. Thank you. Good. Okay. So, right. So this lives in two n variables, x1 through xn and y1 through yn. And so this is a simplicial complex on two n things, which I may as well just identify with the variables x1 through xn and y1 through yn. Okay. The fact that it's square free in every term order is already kind of nice, but the very nice thing is that this doesn't change the shape of the minimal free resolution. This is, you know, the vectors, the dimensions of the tors are upper semi-continuous. You expect them to go up if I do something like take an initial degeneration, but in this case, they don't. This is brilliant. This comes from the Cartwright-Sturmfels ideals notion of Ponca, de Negri, and Gorla. But that is the other key thing, that this has a free resolution of the same shape. Of the same. So in particular, you can get the dimensions of all of these wedge products still out of tors of this thing. And then you, okay, well. How do we do this? I have to say a bit about how we do this. Well, I'll say the last of the proof. Yes, okay, I'll say that the last thing we do is okay. If you have a simplicial complex and you want to inspect certain tors, you can pull it out as using Hochster's formula. It writes the thing you're looking for is the sum up to some sign, the sum of the dimension of homology of some links and some complexes, dimension of homology of something is positive, and you check the signs, and the signs work out in this case. I think you want the sum of like the dimension of H something of H something of link somewhere of the complex. Okay. One thing that we need to do in here to know which homological degree we need to look at. If there's more than one homological degree involved, we could still have some sign alteration here, and this would be no good. The way we show that there's only one homological degree is by reducing to the case of the matroid Schubert variety. How do we do that reduction? Well, kind of the key thing is that, the key case, if one of my linear spaces is a line, say it's just the line through the 1, 1, 1, 1, 1. That's the nicest line to work with. Then my y L1, L2 is the matroid Schubert variety. L1. Why is this, right? Okay, so what have we done here concretely? Well, these things, the fiber of the identity is L1 direct sum L2. So if I take a point in the collapsing, which came from the fiber of the identity, I have a point of L1 and a point of L2. Maybe I have to say co-order. Okay. If I take a point then I get something for L1, something for L2. If I translate this by the torus, then I get I define these bundles T equivalently, so I have to act on this thing by T. I have to act on this thing by T. And okay, the torus is a dense open in here, and so closing it, the worst that's going to do is take the closure of this set. This is closed, so in fact, this is a description of what I get. This two linear space Schubert variety can be concretely described as this orbit closure. Okay, so now if I take the second linear space to be 1, 1, 1, 1, to be like the identity in the torus, okay? If I take that, C times all ones, well, I get the closure of T times U and T. Which, well, okay. Now if I projectivize, right, the matroid Schubert variety lives in P1 to the n. Here I have something that lives in C2 to the n. So I should really decode. I should go back down to P1 to the n by interpreting these as projective coordinates. What do I get? Tu, right, like Ti, Ui, colon Ti as projective coordinates. U in L, T and T. I can cancel these T's, so this is just, a point in L within P1 to the n. Right, so it's the closure of L within P1 to the n. That's the matroid Schubert variety. So the matroid Schubert variety is the case where one of our things is a line, which, kind of has two functions for us. First, we can look at the combinatorics from the Ardila-Booker paper that introduced the matroid Schubert variety and try to replicate it in our case, right? They can say what this is for the matroid Schubert variety. This is an external activity complex. And so, that makes our task clear. We have to figure out what the external activity complex should be in this setting. So that's, we use it both kind of analogically and directly. We actually use it, the Cartwright-Sternfels ideal machinery says if I have two ideals with the same Hilbert function and one is a certain kind of generic initial ideal of the other, then I can, convey properties between them like shapes of free resolution. So we actually compare our ideal to a matroid Schubert variety ideal and use the Cartwright-Sternfels machinery to convey the shape of the resolution between them. And that's how I know what the correct homological degree to look in here is. Okay. So I got precisely no combinatorics aside from this on the board in my first hour, but at least I will have a little resume of kind of what combinatorics I will do in the second hour and how it will fill this in. So, okay, to come. The first thing is I want to define this thing. This is going to be some kind of external activity complex. I'll need to use this Dilworth truncation en route to doing this. And then the second thing I want to do, right, this was all a proof sketch of the representable case. It was using the fact that I had these actual linear spaces to construct this variety and then degenerating it. I want to do something that doesn't pass through the variety. Well, the thing that we managed to do that doesn't pass through the variety is using a kind of argument by extending by valuativity. We show that the K polynomial, or if you like, Hilbert function, that's all a K theory class is, it's a Hilbert function. You show that the K polynomial of this object is a valuation, okay, like co-valuation, but I have the inclusion-exclusion signs in there now, in M1, and separately in M2, it's bilinear, right? If valuation is being linear, it's a valuation in each argument. And then we can use that to extend the stuff we did to the representable case to the general case, because representable matroids span all the matroids up to valuation. That is kind of the rough shape of what I need to do. So in the next hour, I will define this and show you why I gave the talk that Cockamamie title I did with intersecting Chern classes, because that's how we do this second thing. Thank you. First, okay, let's deal.
So for part 3, you use M1 equals M2 equals M1.
That's right. I mean, if I want to get omega, then I specialize this to M1 equals M2.
And do you use somewhere the more general case, or you have everything with M1?
We use the more general, yeah, I said this but didn't, right? We use the more general case to do like we get a kind of this Cartwright-Sternfels relation between this guy and a thing where I put the Dilworth of 2 copies of M here and a line here. And then I look at the shape of this resolution and pull it back to the shape of this resolution. Yeah.
Where does introducing the 2 matrices, the L1 and L2, where does that idea come from? Like,
I mean, like historically or functionally? I mean, historically it came from like reading this paper of Ardilla and Booker. I didn't cite them, but I should have cited them here.
but they only consider one.
They only consider one.
But I mean.
And we thought we were only considering one, but when we, okay, maybe the real idea where it comes from is that like playing with these bundles, like there is, Andy and I had a sequence of 3 papers before this where we were looking at orbits of a single representing matrix. And you can interpret that as a kind of collapsing of like a big power of the S for a single L. And the kind of, but you do games like this. You have to break it into a bunch of factors and consider the multigrading for each factor. And so I guess once you have several bundles like this, it's kind of, you can interpret the Ardilla-Booker thing as also having 2 bundles, and now they're from 2 different matroids. So those are the kind of hints that it would be sensible to look at 2 bundles for different matroids here. Mateusz was probably first.
So why was 0.0 easy? I mean, why?
It wasn't easy, it's just, I wasn't talking about it. Point zero is an intersection theory, tropical intersection theory, or I guess it's actually tropical. Okay, so Kris gives a formula for this that is the Bourbon class times stuff. So you localize to a maximal cone of the Bergman class, and now the stuff is like a positive thing times elementary symmetric functions in all the Chern roots of Q except for the first one, which is what Junie calls alpha. And so it's like the total Chern class of Q over 1 minus alpha, some kind of thing, but then you massage that thing and you can turn it into a positive combination of omegas once you specialize to a stratum. I mean, maybe I can talk about that too one day, but I did, yeah, okay. I was talking about this here. We'll talk. Lewis.
So as you mentioned during the talk, G is invariant under taking duals. And from this formula for omega, it's not apparent that that property will be preserved.
Right. Well, the way we've defined omega breaks the symmetry. Even if M is co-rank.
But let's assume that the rank is
smaller than
half
rank.
the size.
Yeah, okay.
I mean, do you think there could be an alternative formula that makes the role of M and dual be symmetric somehow, or is it like really necessary to put M?
I mean, if M is half, so the N is twice the rank. I mean, then I guess I can formally do something silly like interchange M and M dual here. Maybe I probably couldn't do most of this with it, but there might be something else you could do.
Yeah.
I mean, this is the behavior of omega is fairly constrained in that case. Omega is plus or minus 1 or 0 in that case. I guess you know this.
Yeah.
If N is 2 times R, so if the matron and its dual are the same rank, then omega is just detecting whether the point 1/2, 1/2, 1/2 is in the relative interior of the matroid polytope or not. So if it's not, you get 0. If it is, you get 1 up to sine, where the sine is this value of sine. This paper gives a more elementary argument of that, but I don't know a way to see it from here.
An older approach to proving the non-negativity
Yeah.
in the representable case, there was some Kodaira vanishing somewhere.
Right.
What happened to that?
It got hidden in the preconditions to apply step 2 here. So I mean, the first thing we're using is rational singularities. So there's your first appearance of characteristic 0. It's kind of okay. What did I hide here? Binglin Li says that this thing is multiplicity free, right? He writes down the multi-degree of this thing. Okay, and then there's a paper of Brion which gives some cohomology vanishing for multiplicity free subvarieties, and that is, that's not the Kodaira vanishing, but it's similar characteristic 0 specialized techniques. And then we use this paper of Ramanathan and another author to push to the section ring, and then we do this. So it's kind of I buried that in the preconditions of this, but it's a bunch of rational singularities flavor games that we have to do to apply this.
And in the end, like the Euler characteristic has the right sign because all the cohomologies are 0.
Because all the cohomologies are 0 except for like the one of them that corresponds to the rank of the flat you're trying to pick off, and that has the correct sign.
Okay, to be continued.
To be continued.